So welcome back to today's lab. This will be the final lab, and essentially what we're doing is we're going to look at implementing a binary tree, but we're going to do it over an array. So rather than using nodes and pointers and creating that tree structure that we've grown accustomed to, we're just going to use an array, and there's going to be a couple of properties which we would need to adhere to. And that is that the root node is going to be located at array index 1. Array index 0 is going to remain unused, and the reason why we need this to be unused is because left children of any parent is going to be stored at index 2n, whereas right children are going to be stored at index 2n plus 1. So that's fairly simple. If we want to take a look at what that would look like, and I'm just going to use this input sequence that I've taken from the lab exercise. Let's say we've got our first element 5. It's going to be the root, so it's going to come in here and sit at index 1. So that would get stored there. Element 4 is going to be a child of 5, and it's going to be a left child, which means it's going to get stored at 2n. So of course 2n, 1 times 2, it's going to get stored here at 2. Element 3 is going to be a child of 4. It'll be a left child, so that'll get stored at 4 because that's going to get stored at 2n of 2. 7 is going to be the right child of 5, which means it's going to get stored at 2n plus 1, so it'll get stored here. 6 is going to be the left child of 7, so it's the right child of 5, and then it's the left child of 7, so it's going to get stored down here at index 6. 1 is a bit different. It's going to get stored at index, it'll be the left child, and then the left child. So it'll come up here to index 8. Element 2 is actually going to be the left child, and then the right child. So it's going to get stored at index 2n plus 1. So it's actually going to get stored down here at index 17. So there will be gaps in the tree, and that's fine. If you don't have a fully fleshed out tree, you will find there are gaps. It is just a binary sorting on it. So you can see that the last few elements go in. We bring in 12, and then we bring in 9 and 15, which are children of 12. So essentially what we've done is we've created this tree structure here, and we've just flattened it out so that it can be represented on an array. So if we just take a look at the exercise, the first thing they want us to do is to write a class template ABTree, which is going to be our array-based binary tree, and it's going to store pointers to instances of some type of item. So that means we need it to be generic. The item stored at any node of the tree is bigger than the item stored as its left child, so that's just what we were going over before, left and right children. That's the standard binary structure that we're applying there. Then it's just got some member functions. So the first one we need is add, and we're also going to need search, and then we're also going to need size. I haven't done the video on search yet, that's coming up, but it's really similar to add, so it's not really going to be very difficult at all. So in my implementation here, what I've got is, you can see I've got ABTree, and I've just got my constructors, I've got a destructor, we've got add and search and size, which will return the size of the tree. Because it is going to use those recursive functions, I've got an ABTree add and an ABTree search. So for the implementation of ABTree, it's pretty simple. If you take a look at your constructors, all we've got is we're creating that new item array and we're setting it to the length 40. Could use a final there. And then in this case, we're setting the tree size to 0. In this case, we're setting the data as that root element and setting the tree size to 1. Then of course we've got our destructor, pretty simple and quick there. When we're adding items, essentially what we're doing is we're taking in data of what needs to be added. If the tree is empty, then we're going to add that data and just add it at the root. Otherwise, we're going to send it down here into the recursive function, and that's going to help us find where to add that data item. This function here is essentially exactly the same as what we looked at last week, except we're using an array. So the first thing we need to do is just assert the length, just make sure that that index here is not actually out of bounds for what we want to use. Then all we need to do is just say, okay, if the data at this index is less than the data that we're trying to add, then we know we want to add the data to the right side. Then we just check that the array-based index at 2 index times 2 plus 1. If that is null, then okay, we definitely want to add that data. And then we can just return. Otherwise, we're just going to return the call and we're going to go through, and this is like returning to the right child. We're just going to go, okay, we're going to add, we're going to go to index times 2 plus 1, and then we're going to add that data. Kind of the same on the left side, just all we're doing is storing at index times 2. And yeah, that's it. That's the add function. It's really simple. Search function is pretty much just as simple. For our search function, all we need to do is return the index of where that item is stored in the array. So we're just returning an int. So we come in, we go down, we make a call down to the recursive area. We're starting at index 1 because that's our root. And then essentially, if the index is less than 40, then we know we can go through this case here. And this is the case where, okay, if the array-based tree, if the item at this index equals the data, then we've found the item. Otherwise, we've just got to search to the left or right as needed. If we've gotten to the end of the array, we can return -1 and just use that as our flag for saying that the item was not found. So that's about as difficult as today's lab exercise gets. It's really quite easy. I've just dummied up a little thing here. We're just inserting that sequence that they've asked us to insert, and then all I've done is I've seed out to see where element 6 is, where element 15 is, and where element 17 is going to be stored. So if we just run that, which I've got over here, you can see that item 6 is stored at index 6. Item 15 is stored at index 15, and item 17 was not found. So that was a quick demonstration of tasks 1 and 2. What you can do for task 3 and 4 is you just need to look at prefix, infix, and postfix, and that's the stuff that I was showing you in last week's video about the ways to traverse the tree. We just want you to write some pseudocode for that. Just have a go at how you think those would be amended to work for the array. And what you would do is, rather than starting at the root, you're actually going to start it from any element, which is element V. So yeah, just have a go at that. And then if you want to continue, you can also have a go at implementing the infix search and use that to print out the contents of your tree. So that's just looking at that stuff that we did last week and then changing it to work for an array.